Hello, everyone. Thank you for joining us. My name is Miki Haimovich. I'm VP Business Development with RSIP Vision, a global leader in computer vision and deep learning. For this webinar, I will host Moshe Safran, our VP R&D. Hey, Moshe.
Hi, Miki. Hi, everybody.
Thank you. And we will be discussing project management for AI implementation in medical devices. A few words about RSIP Vision for those of you who don't know us. We are providing AI and deep learning solutions for image analysis only, I must say. We don't do NLP or genomics or anything like that. The solution is customized based on your project needs and your data set. We've spoken about it a lot in previous events. I'll say it again, that this industry is very far from standardization. So the chances you'll find an off-the-shelf product that fits your exact needs are pretty slim. So we take a different approach. We start with you and with your project. We understand what you're trying to achieve. Then we have a look at your data set, and then we customize, we tailor-make a solution that fits your exact needs. We've been doing that for over 25 years with multiple repeat clients in the USA. We have extensive experience in all AI and deep learning techniques in numerous medical applications. Some of them you will see today. And we have an experienced team of over 45 engineers located in Tel Aviv, Silicon Valley, and Boston. In addition to those, we have a medical team in staff to guide solution development, including radiology, pathology, and more. So the bottom line is that in case you plan to develop an AI solution, RSIP Vision is the safest, most stable way to do it. We have an experience in broad range of AI applications. I'm not going to touch upon each and every one of those examples, but as you can see, we've touched upon pretty much every modality out there: CT, ultrasound, X-ray, MRI, OCT, pathology slides, microscopy slides, and so on, as well as most organs in the body. You can see chest, you can see heart, bones, spine, and so on and so forth, as well as most types of tissues and staining out there, and so on. A few words about our development process. The development process starts with a proof of concept, and this is for two reasons. The first one is that we are, again, since this is not standardized, when we just start, we need to learn about your project and your data set. And having the proof of concept enables us to do so. The second one is that once we get to know your project, then it's easier for us to quote you and estimate the cost and the timeline of that project. The first step is to sign a mutual NDA or CDA, makes everybody feel more comfortable. Then we define what parameters and deliverables are needed from the POC, and then the customer provides samples. They don't have to be annotated. We can deal with the annotation, and they don't have to be plenty of samples, okay? A limited number of samples is very much enough in order to start the process, in order to start the proof of concept. Once we have all of those, then we start developing the POC level solutions. This is an iterative process that includes weekly discussions and updates regarding the solution development. You're part of it, we're just doing it for you, and this happens as part of a conversation. It usually takes a few weeks, between 1 month and 2, it depends. And once we have the POC ready, we present it to you, we present it to the relevant people in your organization. At that stage, we can also send you the quotation and discuss the costs and the timelines. And once we have the green light, then we define the fully developed solution. Of course, RSIP develops it, and then, of course, this again takes place in weekly discussions and updates regarding the solution development. Okay, again, we're doing it for you, and this is all part of the conversation. All in all, as you can see, the process can take several months, but it means that after these several months, you can have an up and running AI solution customized to your needs, integrated to your medical device. So that was a little bit about us. And now let's speak about the topic of the day, challenges in project management for AI implementation in medical devices. Moshe will take it from here. Moshe, the floor is yours.
Okay, hi everybody. My name is Moshe. I've been creating and managing development of AI and computer vision algorithms for over a decade, currently leading the R&D at RSIP Vision, and soon to be leading our efforts and our operations in the US out of Silicon Valley. So I'm going to talk a bit about interesting challenges in project management for AI and computer vision in medical devices. Okay, so I think we're all familiar with the deep learning revolution in computer vision. A large part of the academic work is in this field, and the industry is re-examining current products with a new approach and many success stories. I was just at the CVPR, Computer Vision Pattern Recognition Conference, it's still called that, in LA, and just like a week or two ago. And really, there are 3 tracks there, and 2 of them are completely deep learning, and the third one is like 3D geometrical type solutions. There's a huge wave of startups, and many things that have not been possible in the past are really becoming possible, which is great for all of us. Now, for project management, obviously just typical sort of waterfall style or other style charts are too general for computer vision and AI projects. We're not, building a house or a car, and we're not even building software. We're really developing algorithms, which calls for a different type of project management process. So, yeah, so just wait for the slide to advance forward.
In the meanwhile, I'll take this opportunity to ask everybody to send us questions. Okay, you can send them as we go along. You don't need to wait for the Q&A session at the end of the talk. Please share them with us, and we'll be happy to answer them at the end of the session. 1 second. It's not working. Okay, Moshe. So I'll take it from here with regards to the slides here.
Okay, so 12 tips for an AI and computer vision project manager. Yeah, this is really, it's a very interesting challenge to manage these projects, and there's lots of things we've learned over the years that we'd like to share with you. So tip number 1 is review 100 images. So you would think, it's all deep learning, it's AI, you just throw it in, you get a lot of data and it works. It's not true. That's not how things work in the real world. Our CEO, Ron Safran, likes to say that saying that we do AI or deep learning is like saying we use software or we use programming languages. So of course we're using AI, but for a project manager or even a team leader or a developer to really understand what they're up against and what they're dealing with, you need to review at least 100 images or some representative set. In the medical field, you should always involve a clinician and understand what kind of data you're dealing with and what the various cases are. And yeah, this is an example. So we actually have a product of a automated resist read. It's called of detecting nodules and lesions and cancer cells in the lungs and in other organs of the body. And it's very important to understand that there are different varieties of lung nodules with different absorption properties, which affects the way they look in the CT. And you need to understand this by looking at the data visually. They're solid, subsolid, pure ground glass. You need to have a radiologist on board to understand this and to balance the data set correctly for the training, and understand later on your failure cases by really seeing visually what's going on. Tip number 2, create a team for new ideas. Again, everybody's using deep learning and neural networks, but it's not just software, it's not programming. It's quite important to have an interdisciplinary team. You need to borrow techniques from math, physics, signal processing, statistics, and of course, computer science. You need a team really who is going to exchange ideas and brainstorm about things and bring a variety of types of expertise to the table. So this is still true today, even in the age of AI. This is an example of karyotype classification. So the input is an image where you see chromosomes, and the goal is to sort these chromosomes and to find the pairs, to see for a Down syndrome diagnostic application. So there are a few stages here. There's the segmentation stage, which the leading technology for is the deep learning, UNet, PSPNet, etc. There's a classification stage, but afterwards, to do the pairing correctly, you need to add on a graph matching type algorithm, not a learned algorithm, unsupervised algorithm that finds the optimal solution based on the guesses for the classification given by the neural network for each individual chromosome, and then later finding the optimal pairing and understanding the full picture of the whole set of chromosomes in the image. And there are many more involved examples than that. Tip number 3, deep learning is not just a black box. There's many ways to implement it, and in many cases, it still makes sense. So, you see here in the picture, it seems simple. There's an input, you put it into some machine, you train it on labeled examples, and you get your output. It's not always the right way to do things, and it's still important to understand the problem, to think how our visual system processes this as people, how we understand what's important in the images, what's not important, and in many cases to split the problem into intermediate stages and take the most effective results of one stage and use them for the next stage. In the next slide, we can see, again, a sort of simple example for this. The application here, this is an X-ray image of a spine vertebra. The application here was to find the corners of the vertebra very precisely, to millimeter precision, even sub-millimeter precision. And what we found is that the best way to do this is to divide it into stages. First do rough segmentation to find each vertebra, and then a regression type of solution to find the corners of the vertebra. Naively, one could think of this just as a general purpose detection problem. You have the whole image, let's detect any number of vertebra. But for the data set that we had and for the conditions we were working in, we found it was actually a more effective solution and a quicker to implement solution to divide the problem into 2 intermediate stages such as this. So usually you can say, yeah, this is a problem we've seen already. There's one image you need to detect. You need to think of it as a detection problem, but that's not always the most effective solution in a given situation and given time constraints on the development. Tip number 4, always deliver from POC to validation. This is true, of course, for any software development, probably in other industries as well. But for us, it's very important at the POC stage to start with something. You want to deliver an initial solution that's doing some useful work, some working software. And this is important, to gain confidence from both sides that the project is possible, to prove the concept, so to speak, but also beyond the need to achieve a proof of concept and convince the various stakeholders that the project is feasible. It's also important to understand and to scope out the problem correctly. The way to really understand a given project and to scope it correctly and to plan for it correctly is to get your hands dirty, so to speak, with a limited proof of concept, with a clear deliverable at the end in their time frame. Yes, so as Miki said, a proof of concept stage is usually a few months, and we aim to deliver something at the end of the concept, but actually something should be delivered every week. Or every 2 weeks at most. This is, the typical agile development dogma, so to speak. You have a sprint, and the sprint has deliveries. Now, in algorithm development and in AI, what delivering something means can vary. Delivering something can mean you're delivering working software or software updates. This may not happen every week, but the delivery can be a literature review. It can be initial results. It can be some stub. It could be code refactoring on the software side. It could be, analysis of the results, validation. It can be a variety of things, but it's important to have some clear result, even at this smaller, higher resolution within the project. Tip number 5, what happens when it doesn't work? It doesn't always work at first, when deep learning fails. So tip 5A is don't jump to conclusions like more data, more complex algorithms, new architecture, new method that seems cool that somebody read about in an interesting paper, even if it's by a leading researcher. You don't want to only think of the problem sort of from the outside, or to think of everything as a general purpose machine learning problem, overfitting, underfitting, etc. But rather, it's very important, especially in computer vision, to analyze the problem and the specific problem domain that you're dealing with. Failure analysis, which means to look at the images. Make sure your developers have the patience to view many images and many results and understand what the failures are. And this is going to feed back into the algorithm development process, whether it's in the data set management, in data augmentation, or in many cases, into the architecture and algorithm itself. Of course, you also need to check code validity, bugs, input images quality. You know, sometimes you look at the input images and you see in some of them the information is just not there. It's very important to always to keep looking at your data, and annotation consistency is also very important. You need to really verify that the problem is well posed, is well defined, and that the annotations are consistent and agreed upon by all the stakeholders involved in the annotation process. Yeah, this is an example. So again, we saw lung nodules. They have various appearances. However, for an untrained eye, the image on the right might also look like a tumor or a growth, but really it's just water. And you really need to involve, in this case, a radiologist to educate and coach the annotation teams to understand what it looks like, what nodules or the lesions look like, to annotate it correctly, and also understand this not only on the annotation side, but also on the algorithm development side, in order to create the proper architecture and proper algorithmic solution that's going to solve this problem. Yeah, AI and false positives. So in the medical domain, in some cases, if you have false positives, it could kill the product, because if you're trying to diagnose something and your false positive rate is too high, then nobody's going to want to use this, because it's going to cost the users or the insurance companies or the providers too much money with all these false flags. And of course, the task can be quite complicated. So this is an example of a diabetic retinopathy. On the right, a positive image with various lesions of various appearance. On the left, a normal retina. These are pretty easy, so to speak, to tell apart by eye, but you can have many false positives that can look like lesions, especially due to the variability in these lesions and their appearance. And you need to be aware and fight back, so to speak. Okay, tip number 6, and this again, everybody who's in software, you can be developing an office suite or a database or whatever, or a website, and you still find this happening. And we're no exception as algorithm providers. We also find that the specifications, in many cases, are changing and evolving in parallel to the project. And this sometimes needs to lead to algorithmic changes. The performance requirements can change during the course of the work. As a service provider, you can't just say, "Oh, we didn't know." You need to adapt, and all sides and all stakeholders need to adapt as well as possible and come up with constructive solutions as best as they can. The input data can change. The data itself is typically being collected in parallel with the algorithm development. We're not waiting in many cases for a full data set to start working. And the requirements in the field are also evolving in parallel. We're delivering proof of concepts and interim deliveries, and this is being fed out into the field or to earlier stages, internally in the medical device company. Then the requirements are going to evolve and going to change, and you need to really plan an agile infrastructure ahead for the project management. Success criteria. These also can evolve over the course of the project. It's important to understand what the use case is. What is the price of false negatives, and what is the price of false positives, and to guide yourself in accordance. What are the final measurements? How is this product? How is this module really going to be used in the field? And communicate well between everybody to understand what the correct success criteria is. This is a simple example, again, a brain tumor multiclass segmentation. There are various tumor areas, and you can't just use, average dice coefficient or something similar, because Some of the classes might take up much less volume, smaller volume than the other classes. It doesn't mean they're less important. You need to count your voxels correctly. Just a simple example of success criteria. Tip number 7 in project management. So the effort should be in proportion to the size of the data set. This means if there are only a few samples, you want to manage the risk of overfitting. You don't want to, before you have enough data, or at least as much data as you ever expect to have, you don't want to work too hard, so to speak. You don't want to overfit to it. You want to start with an initial working algorithm, concentrate on validation and software, and save, most of your tweaking of the networks and of the architectures and all the fun algorithmic stuff to a stage when the data is really there in the form that it is expected to be in the real world. Okay, tip number 8, what to do if your project is running behind schedule. You might be surprised to hear that sometimes this can happen. So what is the reason? As team leaders and managers, we need to understand what's going on, and there can be a wide variety of very different reasons for a project running behind schedule. And even if we're very deeply involved in the technical aspects of the project, this requires some intelligent thinking and analysis to understand. Is it because of programming skills that are missing in the team, analytical capabilities? Sometimes no, sometimes it's the ability to converge. So these people can all be geniuses, they could be great, but are they managing their time and their choices in terms of what to do and what not to do in accordance with the schedules and the deadlines? Data preparation, is the data being prepared correctly? Maybe that's holding everybody else up. Feature creep, is the scope really, does the scope of the project really make sense to deliver initial system? What's your MVP? What's your minimal viable product? What's really important, and what should be deferred in terms of scope in order to reduce risk and reduce the number of changes, especially at critical times when deliveries are important and need to be stable. And of course, separate research from development. So if you have a bigger team, obviously what you can do is you can parallelize it. You can have some people who are closer to the deliveries themselves, closer to the software, closer to the validation aspects, and they make fewer changes. And you've got other people and other code branches doing a more research-oriented track in order to reduce the risk and still involve and still devote effort to the more deeper solutions for the long term of the task. Tip number 9. Algorithmic design documents. So this is just an example of one document that's used for these projects. There are many others. In a way, there's a slogan: if it's not documented, and it's not done. So it's not that extreme in all cases, but it's important to write down what the assumptions of the algorithms are, what the parameters are, what the successes are, and communicate and follow up. Keep it concise so that you don't end up wasting your time on writing more than is necessary. Keep it relevant, and what you are, the algorithm development design document that you are keeping live, keep it updated. So this requires some careful thought and prioritization. Tip number 10, Python or Matlab to C++. So this really depends on the family of algorithms. So if it's just a neural network, Keras, TensorFlow, whatever, usually this is relatively easy, so to speak. So there are certain technical steps that need to be and measures that need to be taken, but sometimes it could be easy. If you're starting to create more hybrid algorithms or even combining just various networks that you trained under different frameworks, which sometimes is more convenient, you need to understand, and especially if you're adding pre-processing, post-processing, classical algorithms, 3D, etc., you need to understand what's consistent. Many times we do perform the research in Python, or in the past labs in Matlab, because it lets you create prototypes very rapidly. But then afterwards, when you're porting it to C++, you need to understand how to measure the consistency. What's the correct way to measure it? You don't always want to do bit exact. Sometimes you need to do bit exact. Sometimes you don't. you try to use the target platform sooner. So even if at early stages you're not doing everything in C++ and you want freedom for research and for prototyping, etc., it can make sense in many cases to cut off some piece of the project and do that at C++ at an early stage so that you understand the integration challenges, etc., in advance. And of course, there's the issue of network compression, which goes along many times with moving to lower level programming languages and also changing the architecture of the networks themselves. Tip number 11, adjust your project management to the families of algorithms you're using. So the first bullet on the left side says deep learning, and it's in bold, and there's a good reason for it being in bold, but there's still plenty of use for other algorithms as well, heuristic algorithms, even sometimes classical machine learning, and definitely tracking, etc. And the project manager, the team leader, needs to understand how much data do we need for a given family of algorithms? How does development converge? How fast is it expected to converge? How scalable is the algorithm for a given solution and given data? How well is this thing going to generalize? How well is it going to scale up for larger data sets, if at all? How do you validate it? How do you change it? And how do you maintain it in the future? This all should inform the choice of the type of solution. Yeah, and tip number 12, as we said, is still use a variety of tools, whether it's machine learning or computer vision. Again, neural networks and supervised learning is definitely the leader for many of these tasks. But in the real world and in the medical devices world, it's not always possible, and in terms of the amount of data, and also in terms of the challenges themselves. Sometimes in terms of time frames, and you really still need to familiarize yourself as a team leader with all possible methods. And there are still cases where deep learning is inferior to non-neural network computer vision. If you need to measure something very precisely in the images, you don't, or do subpixel, etc. You don't always want to stop at deep learning. Maybe you want to do detection or segmentation with deep learning, and then do something more mathematical modeling based, so to speak, to do the final mile or the final, nanometer, so to speak. Pre and post processing is important. 3D reconstruction, model-based methods are still being used in some fields. Registration and segmentation, especially registration, is still done in many cases with non-neural network methods. I think in the next slide we have probably an example of it. Oh yeah, and of course, so remember, deep learning is like a 5-kilo hammer or a 10-kilo hammer, so to speak. It can't always replace a screwdriver if that's what you need. Yeah, so here we see an example of registration of retinal fundus images, stitching them on a sphere using features and key points. For this type of task, neural network is way overkill, and it's more experimental type technologies to do this kind of registration with a network, and you don't really need it, and you're going to end up spending too much time in making this thing work and getting enough data to make it work. And feature points, key points, and then applying the correct mathematical analytical model to the geometry is a much more effective way to get this task done, and in a reasonable amount of effort. And in some cases, of course, we leverage deep learning in classical computer vision. This is an example of a research we've done in a retinal layer segmentation. In the next slide, I think you could probably see the results of this. So yeah, in the past, before deep learning, you could get the top layer and the bottom layer, the RP and the ILM, and maybe some of the layers in between. But as we see, this is a very challenging problem, and trained experts are able to get 8 or 10 layers, and that's only been possible after the advent of deep learning. Still here, we at least found that the best way to solve it is to do some combination, to do some pre-processing, edge preserving smoothing filter. Only after that to learn a segmentation problem for each layer. And then the last mile there was done the dynamic programming type algorithm, Dijkstra algorithm in D to find the optimal path in image C, which is of course much cleaner than the original image. Of course, you can mix and match here, and there are different architectures that can achieve this. But we did find here that at both the pre and post-processing stages, the computer vision methods were able to sort of operationalize the constraints that we know that exist on this problem and get a better result with less data. Okay, so to summarize, you need to plan the project correctly, you need to define it correctly, and your work is not done. After you've done that, you need to really keep your eye on the ball in validation and in managing the project and in adapting to changing conditions. We covered 12 tips to lead the R&D team. And if anybody else has any other interesting tips out there and would like to share them with us, we'll be very happy for you to shoot us an email, and we may just fold them into our next presentation. So thanks, everybody.
Excellent. Thank you very much, Moshe, for this talk. And now we've reached our Q&A sessions. I'll start with the questions we have, but again, feel free to ask us more questions. This is really for you, so don't hesitate. Whatever you want to ask. We'll be happy to answer it now, or if we run out of time, we'll get back to you privately. So let's see what we're being asked today. 1 second. Well, many questions regarding the slides and those insights. Then yes, we will be able to send you the recording of this webinar. So, you know, don't worry about it, okay? And you can definitely ask additional questions in addition to that. Let's see what
YouTube, right?
Again?
We're gonna be on YouTube? We're gonna be on YouTube?
Yeah, exactly.
And on RSIPvision.com.
Yeah. Question number 1. Are there any formal training courses to learning AI product management? Well, that's a good question. As far as I know, there aren't. Which is one of the reasons why we've initiated this talk. If you want to learn more about it, and if we've mentioned YouTube, then feel free to jump on our YouTube channel. You'll find not only this talk later on in a few days, but also other talks, mostly by Ron Sofferman, our CEO. He loves project management, and he loves AI, and he loves teaching people about these two subjects. So I believe there would be at least 1 or even 2 or 3 lectures about it on YouTube. If you have any specific question that we haven't answered, or you would like to hear our opinion, then feel free to send us an email, and we'll be happy to help.
Yeah, I'll just jump in and plug our computer vision news as well. We have a monthly newsletter, and there we also usually put in a project management tip. And these tips are, in most cases, based on real experience of our team leaders from projects in the field. So that's useful. As far as the more deep and serious course in project management, I think it's a great idea. I agree with Miki. I haven't really heard of courses for this, and there are so many courses, for AI implementation, for algorithm development, and there's, the Stanford University course that they put online, which is a great resource for people. And in Israel, there are people who are actually taking that course and turning it into a hands-on course, but that's really for the developers. And for project management and AI and computer vision, I think you may have just thought of a great idea for a startup, because I also have not heard about a course such as that, but at least not a real, hardcore one. But if you hear of one, then let us know as well. Maybe we'll send somebody there.
Excellent. Another questions, what do I do if I don't have a multidisciplinary team? It's a good question. Moshe, what do you say?
Yeah, I would say, so there are a few things you can do. First of all, I think if you need to recruit only one person, take them from computer science. That's the basics, software, and people who've, done AI courses. First, you need to, have people who could do the hands-on work, even technically. Yeah, you know what we're going to say. We're going to say you can outsource it, but it takes time to build this type of team. I would definitely, the first developer should probably be from computer science, and then
Excellent.
afterwards start
I would
people
add
from
to
physics.
that
Yeah,
again, feel free to talk to us, because when I
Miki, hello. Okay, so it seems that Miki is experiencing technical difficulties. I can't hear him. So either you can hear me or you can't. So again,
hey,
as Miki said, yeah, okay, you back?
yeah, hello.
Yeah, well, I didn't hear you for about 30 seconds there.
Okay, so I'll continue. I'll say it again. Um, the question is, how do you define success for AI to perform medical diagnosis? Say a human expert disagrees with your AI results. How do you proceed in that case? Okay, so that's a very big question. A few ways, a few possible answers. Firstly, with regards to the human expert, human experts often disagree between themselves. Okay, there's a lot of research about it, and if you're particularly interested, I can send you a few examples. But two radiologists would often see a tumor in two different ways. The same thing goes for pathologists and any other expert. And these are not necessarily things that you can solve by taking the experienced radiologist or pathologist. Two experienced radiologists would still disagree in many cases. So that's just how it is. Okay, our role to some extent is to try and copy, okay, what you, the customer, define as the truth. Okay, we call it the source of truth or the ground truth. And this is something we deal with, especially as part of the annotations, okay? Namely, that we can help you do the annotations, but once we do the annotations, we still need your okay to say that these annotations are according to the way you see things, okay? So in this sense, we're not gonna solve, the disagreements between people. We will ask you what is your ground truth, and we will imitate that. So that's one thing. Having said that, many times AI is able to reduce the number of errors, okay? Because once you train the platform and you make it robust, it will be more accurate rather than less accurate, more accurate than the average physician. Again, there's a lot of research about it. I can send a few samples to those of you who are interested. But that's another thing we should take into consideration. And the last thing is that oftentimes, even if just for FDA reasons and regulation reasons, our goal is not to produce something that is 100% accurate. Okay, it's not that we would love that to happen, but there is a lot of value in that in such a solution, even if it's not 100% accurate, and that is because the user is using the AI solution. Okay, we do not replace the humans, but rather we help them. So if an AI solution can reduce the number of mistakes, if an AI solution can save time for the user, then that's a significant value, even if it is not 100% accurate in all cases. I think that's that's most of what I had to say about it. Another thing I'll just add is that many times, and that is also true for humans, you will find yourself in a situation in which most of firstly, the AI solution, but also most of the human experts will be very much accurate in, let's say, 80% of the cases, but there would always be these 20% of the cases or 15% of the cases, depends what you're dealing with, which are like, esoteric scenarios, okay? And with those, both humans and AI solutions might prove themselves less accurate. And we know that, okay? We try to solve that by having the annotation and the samples as robust as possible. But that's again something we take into consideration, and that hasn't been considered a problem in the past, or at least so far by our customers. It's been a very long answer, but still, Moshe, do you have anything to add?
So basically, as Miki said, the gold standard is the human expert. There's no doubt about it. And if the human expert disagrees with the algorithm, then you want to fix the algorithm so that it agrees with the human experts to as high a percentage as possible. That said, as Miki also said, you need to measure the inter-observer variability. So the humans, the gold standards, the human experts do not always agree with each other. This is measurable. You can do statistics about it. You can understand what are the types of cases in which there is agreement or disagreement. And then you say, okay, if there's a large inter-observer variability, we're going to aim for human level performance. So really the gold standard is the human observer, but it's not always only one human observer. It should be the statistics of human expert evaluations as a whole.
Thank you, Moshe. Okay, another question. How many samples do I need in order to have an AI solution developed? That's a very good question. Very good question. And the answer is it depends, okay? It depends because it depends on the data set, it depends on your project needs, it depends on many things. I'll just say two things. The first one is that in order to start the process, you don't need so many samples. Okay, for the POC, you don't need many samples, and you with not too many samples, you can still we can still develop for you an AI solution that would be sufficient. Okay, so that's one thing. The second thing is that that question often comes along as we plan the timetable or the timeline for the project. So oftentimes we found it useful to, and as Moshe said, you do things in stages, to define stage one as what we do with the number of samples that we have today. Okay, so if you don't have a lot of samples, that's perfectly fine. Contact us, see what you can do. We will make the most out of the number of samples that you have as part of the stage one or V1 of the solution. Usually, once that happens, you have something quick, you have something that can already be helpful, you can deploy it, and once it's out there as part of your medical device, it gives you more time to collect more and more samples, which enable you to then deal with version 2 and version 3 and so on and so forth. As a more general note, I would say that in many cases, this is how our relationship with our customers look like. We start with the V1, then V2, then they think about something else, and so on and so forth. And we've had customers that have been working with us for years, and it all began with a V1 based on the number of samples that they had at the time. Okay, so that's a general answer. What else? Okay, I'm not sure I understand the exact wording, but there is a question here about, how do you structure the project? As Moshe said, the projects really differ one from another. And yes, I mean, if you're having trouble, structuring and thinking about it, then it means that it's a good thing. It means that you understand that this can go in many directions. My advice would be just to contact us and brainstorm about it together. Many times, a customer knocks on the door and he says, listen, I need this, and I was thinking about doing this that way. And once we have a look at his data set and we better understand his project needs, then we can come up with alternative routes that would eventually meet the same end goal. So it's not something I can write to you as in a to-do list, but definitely the structuring and thinking about the how do we go about it is a very important stage, and we're happy to help you with that. More questions. Let me see. Well, this is pretty similar to what we've already asked. Can you give a more in-depth examples that you use C++? Moshe, what do we say to that?
Yeah, sure. In many projects we use C++, starting from the more generic neural network segmentation or classification projects. That's relatively straightforward. You have your network trained, you have the weights, you have TensorFlow in C++, and once you've done it once, it's pretty straightforward to do it in other cases. And this is from there all the way up to medical device algorithms. For example, okay, so we created a whole C++ based foundation. This is not a deep learning based project. This is a parametric model based project. We have a very complicated cost function and optimizer that's minimizing this cost function using a model based approach to fit a certain model of a medical body to very challenging data, and we created an entire C++ framework in order to represent this cost function, to compute all its derivatives, to do the optimization, and to get to the result. And this obviously sped things up by a few orders of magnitude relative to the original solution in the higher level languages. Another example is we currently have a very big ongoing project for surgical navigation. So there again, it's some of the modules are deep learning, some of them are 3D registration, etc. The research is usually done in Python, but the module that we're delivering to the customer are all written in C++, and they're talking to customers a software GUI that's on top of that in order to run efficiently and more robustly.
Excellent. Thank you very much, Moshe. I think we still have a few questions, but our time is up. So I'll just thank you all. Thank you, Moshe, for the talk. It was very interesting. And please, I encourage you to stay tuned for our next webinars. Our next webinar will be held on July 10th, and the topic will be computer vision and AI in pharma. So all of you who have interest in that topic, please do join us. And the rest of you, just continue to follow us on LinkedIn. If you want to be notified about future events, just drop us an email, and we'll make sure to notify you via email or in another way. And thank you for this again.
Thank you, Miki.
Thank you, Moshe. Goodbye, everybody. Cheers.
Bye-bye.